In this section, what I'm going to talk about is some practical ways of using slopes for real-world data. What we've done up to now have been kind of ideal world data where there's no noise in the data, there were no error measurements, things didn't vary just randomly. That's not how it works in the real world. What happens in the real world is that the data is not smooth, that there's bad data in it due to errors, just random noise, all kinds of junk. So you have to have a way of dealing with that. I mean, the most straightforward way is to simply throw away bad data, but even still, you're going to wind up with some data that really does not follow in a straight line. So here's how you deal with that. As an example, what I've done here is I got some data for unemployment rates, male unemployment rates, and female unemployment rates. I don't know what dates these are from. This is for the US. And over here, I made a chart which will plot the male unemployment rate on the x-axis and the female unemployment rate on the y-axis. So let me start the chart editor, and I'll show you some stuff about this data. Okay, I've got the chart editor up here, and the first thing I'm going to do is show you what this data looks like. The male data, since this is plotting male data and female data, if I put in the male data, it doesn't really make much sense to do that because it's just a straight line. I mean, for every point here, the value of the male data is exactly the same thing as its x value, so it's just a straight line. So I'm going to take that out because it doesn't add anything at all. The female data, though, is what this is really about and what the axis is labeled for. When I put this in, okay, what I'm doing is I'm just changing the size of the point which is plotted from none to something that we can see. And this is what data often looks like in the real world. Clearly, you can see that the data kind of, it has a trend to it, but it's kind of scattered around a little bit. And that's what you would expect because things in the real world aren't perfect. Now, what I can do though is back here in the chart editor for the female data, what I'm going to do is I'm going to add what's called a trend line. And what the spreadsheet will do is it will calculate a line which is the best fit it can make for this data. All right, so when I put this in, notice that what we've got here is a straight line. Obviously, not everything falls on a straight line, so there are outlying points. But this is a pretty good example. Now, the other thing that I did down here is for the label, I told the spreadsheet to use the equation of the line for the label. And that's what this is up here. Now let's look at all of this a little bit more closely. Okay, so here is the formula for the trend line. I just copied it down here so it's easier to see. So what is this telling us exactly? First of all, let's look at this number here, 1.43. What this is saying is that if the male unemployment rate, which is the x-axis, were 0, okay, the y value, which is the female unemployment rate, would be 1.43. So what that's saying is that there is always an offset of 1.43 in unemployment of female over male, okay? And that's what this thing is here. Remember we talked about the y-intercept? All right, this line intercepts the y-axis, obviously at x equals 0, because that's what the y-axis is, at 1.43. However, there's another part to this, and that's this part here, 0.695 times x, about 0.7. So what this is saying is something more subtle. This is saying that for every 1% increase in the male unemployment rate, the female unemployment rate does not go up by the same amount. It does not go up by 1%. It goes up by 0.695. Okay? What that's saying is that while the female unemployment rate starts out higher, as the male unemployment rate goes up, the female unemployment rate goes up at a slower rate. Okay? Now, that's what this curve is. This point here where it hits the y-axis is this 1.43. That's the offset of the female unemployment rate versus the male unemployment rate. The slope of this line, okay, is the 0.695. That is telling you how fast female unemployment rate goes up compared to male unemployment rate. Now I'm going to add a line in for the male unemployment rate, and we can see that graphically. I'm back in the chart editor and I'm aimed at the male data. There are no points there, but let me put a trend line in. This red line it has a slope of 1, okay, and that's what this says up here, 1 times x plus 0. Okay, 0 means there is no offset, 1 means it has a slope of 1. And that makes perfect sense, because what this is plotting is the male rate versus the male rate. Since both numbers are the same, you get 1. But look at this graphically. This red line, which is the male unemployment rate, is going up at a faster rate than the female unemployment rate. And that's because of this 0.695 number here. This slope is less than 1, and that's what you see here. This slope here, the blue slope, obviously is less than the red slope, and that's what the equation is saying. It's saying that as the male unemployment rate goes up, the female unemployment goes up at a slower rate. It's like with velocity. This is like a faster car versus a slower car. Here, however, it's unemployment. So the bottom line of all of this data is telling us that the female unemployment rate starts off higher but decreases more slowly than the male unemployment rate. And as you can see, they cross here, someplace around, 4.5% or something like that. So the point to all of this was to show that even if you have somewhat scattered data like this, which is often called noisy data, you can still get useful information out of it by simply fitting a straight line to it. And there's a whole bunch of math about how you actually do that. But a spreadsheet will do it for you automatically. It's called a trend line.